Hey folks, today's topic is we're looking more at continuity, and we're adding something called the IVT, which is known as the intermediate value theorem. So we'll have two theorems so far that we could apply. If you remember the squeeze theorem, we could be making proofs on the squeeze theorem to help us find limits. And we could also do now this thing, the intermediate value theorem, that helps us find y values. And we'll talk about those later. So just a quick review when we talk about continuity. A function is continuous at a point if these three things are true. The one-sided limit from the left is equal to the one-sided limit from the right, which they are both equal to the point. So in other words, that's proving to me that the point exists. The one-sided limits are equal, so the limit exists, and the limit equals the point. So this is the concise way of proving continuity. In class, most of the time we do it in three pieces. We prove that there's a point, we prove that the one-sided limits are equal, and then we prove that the limit and the point are equal. But if you want to just write this up, that works as well. All right, so here we go. Determine the values at which the function is continuous. So we look for problems. Now, if you have a piecewise function, which is what we clearly have here, you have some extra problems to look at because you have to look for the transitions. What happens as you transition from this curve to this curve? But let's look at the individual pieces first. So does this part of the curve have a, yes, this has a problem. Where does this function have a problem? We know this has a problem when x equals 3. X equals negative 3, sorry. When x equals negative 3, we would plug in, we'd get a VA because I'd have a 1 on the top and a 0 on the bottom. When I plug in negative 3, that causes a vertical asymptote. I wish I would have written that out. Let's write that out. VA at x equals negative 3. So right away, we know that our function has some discontinuities. One discontinuity is going to occur at x equals negative 3. Then I want to look at the other functions. So as I look at the other functions, do we have any problems here? No. Do we have any problems here? No. Why? Those are not problems because those are what kind of functions? Polynomials. This and this are polys. And if you're a polynomial, you are automatically continuous everywhere. So if I know that my function is a polynomial, I don't need to prove continuity. I can just say my function is a polynomial, therefore it is continuous. And then at the end here, we have another problem, right? I noticed that I've got a square root. So I have a problem. My problem occurs for any x's that are smaller than 0. I cannot square root any negatives. That's not a problem here, though, because this part of the graph is only defined for x's that are greater than 4. So x will never be negative. So it actually turns out to be not a problem after all. Oh, not a problem after all. Maybe that, oh gosh, that looks awful, but we'll have to live with it. No tangent problem. I hate it. I got to cross it out. I got to fix it. So it turns out to be not a problem after all. But it's good that we noticed it. It's good that we noticed it, but it didn't turn out to have an effect. Okay, so now we need to talk about what really is tricky in these is looking at the transitions. So as we transition, when x equals negative 2, we need to check continuity. When x transitions from 2 to 2, we need to check continuity. And when my x transitions from 4 to 4, we need to check continuity. And how do we check continuity? Well, that's this statement up here. I need to prove that the point exists, that the limits are equal, and the one-sided limits are equal, and that the point equals the limit. So let's go through. Now I'm going to go through in order. I'm going to go from left to right. So my first problem occurred at x equals -3. So I'm going to identify that right off the bat. So x equals -3. F has F. What do we want to do? Determine where. So we will say F is not continuous at x equals -3 because F has a VA at x equals -3. Now we need to figure out what's happening at -2. So I'm going to look at the one-sided limits. So my next possible transition, next possible thing that could cause me a problem is when we transition from this piece to this piece of our piecewise function. So x equals -2. First of all, is there a point? Yes, because this is included. You see how it's -2 is less than or equal to? So f of -2 equals, so when I plug -2, I'm going to plug it into this one. -2 times 2 is -4. -4 plus 5 is +1. Now I need to check that the one-sided limits are equal. So the limit of f of x as x approaches -2 from the left. All right, so if I'm going to approach -2 from the left, I'm going to use this equation. So plug -2 into this. -2 plus 3 is 1. 1 divided by 1 is 1. We're off to a good start. The limit of f of x as x approaches -2 from the right equals, now this is the same thing as my actual function value, but I still want to think about this. These are all the points that are a little bit on the right side of -2, so I'd plug it into that. I'd also get 1. So my point is equal to 1. My one-sided limits are equal to 1. So we can do therefore f is continuous at x equals -2. Okay, so we know we're continuous for all the rest of the points between -2 and 2 because this 2x plus 5 is a polynomial function. We need to now see what's happening at x equals 2. So x equals 2. All right, so I have to prove that the point exists. So we do have a point because it's 2 is less than or equal to. So I would say f of 2 equals, I can plug and chug, 2 squared is 4. Now I'm going to look at the one-sided limits. The limit of f of x as x approaches 2 from the left. I plug it into this. I plug 2 into there. That's 4 plus 5 is 9. Uh-oh. Uh-oh. Math voice is going crazy here. We know we're in trouble. We know we're in trouble. I don't like to stop at this point, though. I'm going to actually go through and prove the next one, just so I can say what's actually happening here. So now I'm going to plug in 2 from the right. I plug in 2, I get 4. So f is not continuous at x equals 2 because, okay, what's our reasoning? Why is this? The ones that you could say that the one-sided limits are not equal is one way to say this. Yeah, that's probably the best way. Let's just say that because the limit of f of x as x approaches 2 from the left equals 9, which does not equal 4, which equals the limit of f of x as x approaches 2 from the right. And I also like to write at the end of this, see, does that make sense there? So I showed that the one-sided limits don't equal to each other. I also like to write it at the end of this, what's actually happening to my problem. If my left side limit goes to a 9 and my right side limit goes to a 4, what's happening graphically? I'll give you 10 seconds to think about that. You should be able to identify what's happening graphically if my one-sided limits aren't equal. What'd you come up with? This has a jump discontinuity. We have what's called a non-removable jump discontinuity at x equals 2. And so, we checked 2, we got to check 4, and this was actually good. Oh, sorry, everything between 2 and 4 is good because x squared is a polynomial. So we're going to see the transition at 4, and then everything after 4, because our function is continuous for everything bigger than 4, we don't have to check anything here. We still need to see what's happening at 4. So x equals 4. Let's check our continuity. F of 4. Oh, I love it. Game over, man. Game over. I kind of covered it up here, but this says this function applies for all x's that are less than 4. This function applies for all x's that are greater than 4. So we would say f of 4 is undefined. You could also say f of 4 equals dne. Therefore, f is not continuous at x equals 4. I guess I could just write again because f of 4 is undefined, but we just said it right there, so I'm not going to write that all over again. All right, so now determine, this is very interesting. Yet again, you always got to go back. You notice what I did here. I looked at this, and then I looked at the problem again. What did the problem actually want me to do? Determine the values at which the function is continuous. So now at the end, I need to do a little write-up that says where everything is continuous. So f is continuous for all x. Now, there's two ways to write this up. I always like to write it up using interval notation. For all x that are an element of, so where's our discontinuity? Our first discontinuity is at -3, so from -infinity to -3. Union, -2 is continuous. 2 is not continuous, so from -3 until 2. Union, and then 4 is not continuous. 2 until 4. Union, 4 until infinity. Another way to do this, and I'm kind of thinking I wish I would have done it that way, is to just say where the continuity is. So like, for instance, I could say f is continuous for all x not equal to -3, +2, and +4. I think I wish I would have written it up. Obviously, that's a lot easier to write up. Read the question again. Determine the values at which is not, okay, we're not continuous. I've listed that. Then find the limits as you head off towards the infinities. Okay, so as I head off towards -infinity, oh boy, where can I'll try to squeeze it in down here. Limit of f of x as x heads towards -infinity. So I would be plugging -infinity into this function. So that would turn out to be 1 over -infinity plus 3. What's -infinity plus 3? Still -infinity, so that's 1 over -infinity. What's 1 pizza divided by infinitely many people? 0. And let's check the other end. What colors could I use? Maybe a nice yellow here. Okay, what's the limit of f of x as x approaches infinity? I really wish I would have left myself a little bit more room, but I didn't, so we're stuck with this. Oh, geez, sorry, you can't even see that. There we go, how's that? The limit of f of x as x approaches infinity would be 8 root infinity. What's the square root of infinity? Infinity. What's infinity times 8? Infinity. Now, in a multiple choice, a multiple choice test, they would make you try to figure out which kind of infinity it is. But in free response, if this was a free response question, you could just write DNE and call it good. All right. So talk a little bit about open and closed intervals. So we haven't hit this yet. We talked a little bit about it last year, but we haven't really hit it much this year, or hit it at all this year. Okay, so a function is continuous on an interval if and only if the function is continuous at every point on the interval. Okay, that makes sense. Now let's talk about what do we mean when we're talking about an open interval. continuity on an open interval. A function is continuous on an open interval a to b. So open interval a to b, notice we're not including the a or the b, if and only if the function f of x is continuous at every point in the interval a to b. So let's do some examples. Examples of open intervals. Some drawings of some open intervals. So examples of open intervals, I'm going to say in here, I should have written continuous open intervals. Examples of open intervals with continuity, I guess. I don't know how best to say that. I wish I would write examples of continuous open intervals, but anyway. All right, so what's a picture? Let's see, what do we got here? This is A, this is B. Then let's do that again. This time A is closed, B is open. Next one I have a point. I have a hole going to an asymptote. And then I have a hole going to an asymptote that's in the middle, A to B. All right, so let's go through and look at which one of these are continuous on the open interval. So this one. Now, what's nice about an open interval is you don't care what's happening at the end. You don't care as long as there's no holes or asymptotes within the A to B, then we would consider this to be an open, a continuously open interval. So, yeah, you're not including the ends, but everything in between is in there. So this is true. This is a continuously open interval. This is an open interval that is continuous. Now, we included this point, but who cares? Because our interval is open, so we're not including A. We don't care what's happening at A. So this is still, again, a continuous open interval. Same thing here. Now I took the point that was filling in A and I moved it up a little bit to make the holy jump. But this is still, I'm only looking at what's happening between A and B. So this is also continuous. Now we start to get to some asymptote stuff, and this one gets a little bit tricky, but remember, you're talking about an open interval. I'm not including this, and I'm not including this very end, so I can get as close as I want. There is a point all the way up until B, just not at B. So this is also true. The only one that's false here is when I've got a discontinuity right in the middle of the graph. I guess I could have drawn this with a hole too. So like, let's say I went like this. This is A, this is B. That is also false. That is not a continuous function over the interval. The tricky one, I think, is this one, because you feel like the asymptote is making it not continuous, but up until the B, not including B, that would be considered continuous. Now this changes, of course, obviously you think it would, when we look at an closed interval. So continuity on a closed interval. So now we're including our endpoints A and B. This is true. Okay, so it's basically saying if you look at the open interval and you're continuous, that's step one. So basically it's saying you're going to be continuous on the closed interval if everywhere from A to B you're continuous. So if you had an asymptote in the middle of it, if you had a hole in the middle of it, right, that would not be continuous. So that's what this is saying. But then they're also saying that the limit, what would be a good color? Let's go with so remember, this is the limit from the left is equal to the point on the, sorry, I said that wrong. The limit from the right is equal to the point on the left. So you see how that kind of makes sense? I mean, if you want to look at if my interval, my limit has to be approaching, so that eliminates this scenario. If I'm coming from the right, I'm headed here, but my point on the left is actually up here. That's not going to be continuous on the closed interval. Because if I look at this interval including the ends of it, this would be false. That would be a false scenario. And then same thing coming from the other end. This means from the left. And from the left has to be equal to the point on the right. So let's draw a couple scenarios and break them down. So let's see, I've included both endpoints, A to B. I take out one of the endpoints, so from A into a hole at B. I take out one of the endpoints and I add a holy jump. And then let's look at, let's say I include this endpoint, but then I go to an asymptote. And then these two are going to be false again because you're just not continuous at all on the interval. I mean, those are pretty obvious. These are the tricky ones. So this is A to B. This is A to B. So let's take a look. What are we doing here? What do we got going on? So from A to B, is everything in the middle continuous? Yes. Does the limit from the right equal the point on the left? Yes. Does the limit from the left equal the point on the right? Yes. So this would be true. All right, first of all, is everything continuous in the middle? Yes. Limit from the right equals the point on the left? Yes. Limit from the left equals the point? No. So this would be false. This is not continuous on the closed interval. Is it continuous on the open interval? Yes, because we only care about what's happening in the middle. Is this continuous on the open interval? Yes. Is this continuous on the closed interval? No, because as I come to the A from the right, my point on the left is not at the same height. So that's false. And then this is the same thing. We're false here. My limit from the left, my limit from the right approaches the point on the left. That's good. But my limit from the left is infinity, and there is no point at B. So I'm not even including B. This would be a false. This is not continuous over the interval. Okay, so this is kind of a weird way. Hopefully that just kind of makes sense on what I'm talking about with open and closed. That was the highlight of this. If you don't memorize this, I don't remember using this one a lot. I just want you to understand, what do I mean when I say an open interval or a closed interval? Determine the largest intervals from 0 to 3 for which the function is continuous. This is basically saying, this translates into identify, oops, let's misspell that. Identify where f is continuous. That's what that's saying. So determine the largest intervals for which it's continuous. Just write down everywhere that f is continuous. So for us, that would be what? Let's see, we're looking at this thing. So f is continuous for all x that are an element of. All right, so coming from the left. So right here, are we continuous here? Is that point included? Does the limit equal that? Yes. The limit from the right equal the point on the left? Yes. So I'm going to include 0 until 1. Are we continuous at 1? Does the limit from the left equal the point on the right end of that interval? No. So I would say 1, but I would not include the 1. Union with, okay, starting from 1, again, I'm not going to include 1 until I get here. So coming from the left, does my point equal the limit from the left? The point on the right equal the limit from the left? Yes. So 2 would actually be included. Union with, and then now here's where it gets interesting. Most of the time when we include 1, you feel like you should include the next one like this, but that's not true for the other point. my limit from the right does not equal the point from the left on the left. So 2 would not be included in that last interval until we get to 3, which then would be included again. I would encourage you to pause here or rewind this and think back through how I got those answers. It's not so tricky. It's not so easy, but it's also, once you get it, it's not really that bad. All right, what are we up to now? Oh boy, I hate these. I hate this one. I don't remember. A is easy. A is easy. I'm actually going to have you pause here. I'm going to complain for a little bit. You start doing part A. List the intervals for which f is continuous, the largest intervals. That means basically you're just identifying where f is continuous. The next part, I'm not going to worry too much about. It takes a lot of thinking, and I don't remember ever seeing a problem like that. All right, let's see how we did here. On the intervals, list the largest intervals for which f is continuous. So coming from the left, so f is continuous. Hopefully you started way over here because there's going to be a lot of intervals. For all x that are an element of, so I'm continuous, continuous, continuous until I get up to what, -2. So from negative infinity to -2, not included because my limit does not equal the point. Union with, again, my limit does not equal the point. He threw a point in there just to be nasty. -2 until the next interesting thing happens at 2. Okay, at 2, does the left side limit equal the point on the right? No, so we would not include 2. Union with, same thing here, so I'm going to not include 2 to start my next interval. Then we're continuous all the way until 5. Not included because it's an asymptote. Union with, not included 5 because it's an asymptote. Okay, now here's our first interesting one. Do we include 6? Yes, because the limit from the left equals the point on the right. So that would be included 6. We are including that as continuity. Union with, and then on the right, I would say not included 6 until, what's that, 7, 8. 8 is not included. Union 8 until 10. Not included. Union with 10 until 11. Not included. Union with 11 until infinity. Oh, I made it. Barely. Whew. Now I got to try to box it all in. Take a minute, look it over, rethink that, maybe pause it or watch the video again, or just look at it, maybe pause it and just look at your paper and think it through. But if there's any pieces in there, like I got confused on when I would include and when I wouldn't include. And you're basically looking at if the limit from the left is equal to the point on the right, or the limit from the right is equal to the point on the left. That's when you decide whether you include or not include. And of course, you can ask me questions in class if you want to. So I'm going to skip this next part, and maybe I'm making another video that explains this if I find some problems on the actual AP test that correspond to it. But I think explaining it is more is not worth what we get out of it. So I'm going to skip those for now, and I'll let you know in class whether or not we need to discuss it. All right, so let's talk a little bit about functions that are continuous over their whole domain. So I'm talking about if you just identify this function, you don't have to prove that it's continuous. If you identify that it's a polynomial, you can just say the function is a polynomial, therefore it's continuous. So this is probably worth memorizing. Probably worth memorizing. These functions. Some of them you already, dang it, excuse me again. You already know polynomials, trig functions, those make sense. Exponential functions. Now, what gets interesting is when you think about rational functions, root functions, and log functions, those don't feel like they're continuous, but it's continuous for all values in their domain. So let's take a look at rational functions, for instance. Rational functions, what's the domain of a rational function? It'd be from negative infinity until 0, union 0 until infinity. So my function for a rational, remember what a rational looks like. Over its domain, the rational function is considered continuous. Because if the domain is eliminating 0, and so a rational function, which is like, our reciprocal functions, f of x equals 1 over x. So 0 is already eliminated from the domain, so you can actually consider that to be a continuous function. Same thing with the root function. This is not what we would say is a continuous everywhere, but this is a function that's continuous over its domain. Make a sketch of a root function. A root function we know goes something like that. Square root of x, for instance, could be the equation. And so the domain would be 0 included until infinity. So over its domain, the function is continuous over its domain. Same thing with log function. A log function is a graph that only lives f of x equals natural log of x. That's a function that only lives positively for x, but that's its domain. So this function is considered continuous over its domain. Domain is 0 to infinity. Exponential functions, trig functions, polynomials, those I don't think I need to do much proving on. I think those probably make sense. All right, blah, blah, blah. Figure out how do you, okay, so give the intervals for which the following functions are continuous by finding their domain. So basically what I do to prove this is pretty straightforward. Look at the functions and try to prove their continuity individually. For instance, is sine of something, pretend like that's not x squared, just something, sine of something, is that a continuous function? Yeah, it's one of our trig functions. Sine is continuous. What about x squared? Is x squared, cover that up, is x squared continuous? Yeah, x squared is a polynomial, therefore it's continuous. So a real slick way to prove that h of x is continuous is to talk about the continuity of its pieces. So we would say something like this: since x squared is continuous on negative infinity to infinity, and sine of x is continuous on negative infinity to infinity, then h of x equals sine of x, sine of the quantity x squared is continuous on negative infinity to infinity. So we have a continuous function that gets composed. Remember, this is that like f of g of stuff. So if you compose two continuous functions, you're going to have another continuous function. Now over here, it's not so easy. This one takes a little bit of work. And yet again, this is not one of those that I see a ton of, but I think it's probably worth just talking about. So I'm going to kind of take this one down here. So we would say, all right, so let's talk about where natural log is continuous. Natural log of x is continuous where? Well, we just made a sketch of natural log. And natural log is continuous for all function values after 0. So natural log is continuous on 0 not included until infinity. What does that mean about cosine of x plus 1? Well, since cosine of x plus 1 becomes the x value, then cosine of x plus 1 must fit in this requirement. Because whatever we put in here must be greater than or equal to, or greater than, just greater than 0. Whatever goes in here has to be greater than 0. Well, cosine of x plus 1 is already in there, so that has to be greater than 0. So maybe I should say since here. Since natural log of x is continuous on, then cosine of x plus 1 must be greater than 0. Because all these values, which is the same as 0 until infinity, right? Okay, so let's see this. So basically, cosine of x plus 1 must be greater than 0. In other words, if we know that this will never be negative, right? Well, at least, hold on a second. What are here we go. What are all the outputs of cosine? What do they bounce between? They bounce between positive 1 and negative 1. So I know this will never end up being negative because the smallest cosine ever gets is negative 1. And so negative 1 plus 1 is equal to 0. But there are times then that this thing does equal 0. Cosine of x plus 1 will never be negative. But it will be equal to 0 at certain spots. And we now need to figure out where are those spots that this would be equal to 0. So let's just make a sketch. I think that's probably the easiest way to do this. Let's do a quick sketch of cosine. Whenever I do cosine, I'm always doing 4 tick marks. And this time I'm going to extend it a little farther. 1, 2, 3, 4. 1, 2, 3, 4. So this is 2 pi. And this is 4 pi. All right, if you haven't sketched that yet, I want you to try to sketch the cosine curve dotted. Draw it with a dotted line. Okay, let's see how you did. So drawing cosine with a dotted line should look like this. Cosine starts up at 1. I guess I should do some y values. Cosine starts up at 1 and goes downward. Then to negative 1, then back up to 1. So there's one cycle. Then I'm going to take this again. There's a second cycle. Now, what's the function we're talking about, though? We're talking about cosine of x plus 1. So what's that going to do to all those y values? It's going to shift it up 1 level. So now this is my low point. Okay, so I don't want to draw that one dashed. I want to draw that one solid because that's the actual graph. This is the graph of f of x equals cosine of x plus 1. So our question was, okay, let's stop and kind of just reset and sort of what the heck are we doing? Natural log can only have positive numbers plugged into it. You cannot natural log a negative. You cannot natural log a 0. So that puts a restriction on what cosine of x could be. So are there any places where cosine of x is negative? Let me try again. Cosine of x plus 1 is negative, or cosine of x plus 1 is equal to 0. And we just graphed it, and yes, there are many times that cosine of x is equal to 0. So I would draw a little arrow here. X equals pi. That's where x equals 2 pi, 3 pi. Those are places where my cosine x plus 1 is equal to 0. Those are the bad places. So let's see if we can write this up now. So where would the next one be? It'd be pi, 3 pi, where would the next problem be? 5 pi, 7 pi, 9 pi. Let's go the other direction. Negative pi, negative 3 pi, negative 5 pi. So let's talk about how we're going to write that up. So the write-up is actually kind of slick. We would say, so our kind of the logic that we got out of this, so cosine of x plus 1 equals 0 at pi, 3 pi, 5 pi, etc. So our write-up is actually pretty slick. So we would say, remember, we're talking about give the intervals for which the following functions are continuous. Life was good here. Continuity was everywhere. So we would say h is continuous for all x that are not equal to, okay, who was bad news? Pi, 3 pi, 5 pi, blah, 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 blah. The way you write this up is you say, I ran out of room. I'm going to go this underneath. H is continuous for all x not equal to pi plus, now if I went from pi to 3 pi, how many pi's did I go up by? I went up by 2 pi's, and then from 3 pi to 5 pi, I went up from 2 pi's, and then 2 pi's and 2 pi's. The way we write this up is we say pi plus 2 pi n, comma, n is an element of the integers. Now what's so cool about that is when you say n is an element of the integers, that covers everything. I would add 2 pi, add 4 pi, add 6 pi. It covers everything going forward, but it also covers everything going backwards. So if n is 0, I'd just get pi. If n is negative 1, I would get negative 3 pi. If n is negative 2, I would get negative 5 pi. So it covers everything. So basically what I did was I went to pi where I knew my first problem was, and I just kept going another lap around the unit circle, another lap around the unit circle, or I went the other direction around the unit circle. So I'm going to stop there, and we'll do the next video on the intermediate value theorem.